Hi, and welcome to Lecture 12, in which we're going to start talking about Hamiltonian mechanics, another new approach that builds on both the Lagrangian and Newtonian formulations of mechanics that we've already covered. Now, the Hamiltonian approach really builds on the idea of conservation of energy, but it lets us take that approach even further in order to figure out the dynamics of systems. So to define the Hamiltonian H, recall that we start in the Lagrangian formalism. What we do is we start with generalized coordinates qj. Now we're able to define the Hamiltonian as the sum over j of the time derivatives of the generalized coordinates times the generalized momenta, and then that sum minus the Lagrangian itself. And I'll write that as in terms of qj and qj, not gj, qj dot. Now also recall that the Hamiltonian was conserved exactly when the Lagrangian did not depend explicitly on time. And we're going to assume that throughout our study of Hamiltonian mechanics. All right, so this object is all well and good, but I want to make a now further assumption. We know that all of the states that the system can be in can be given by the set of available generalized coordinates and time derivatives of generalized coordinates. So we would like it if those two coordinates, or two n coordinates, if we were in n dimensions, can be written in terms of the n generalized coordinates and the n generalized momenta. So the way that I'm going to write this is that q, let's say 1 through qn and q1 dot through qn dot are a, and I'll use a math term here, a bijective function of q1 through qn and p1 through pn. In other words, for every 2n tuple here, we have exactly one 2n tuple here, and for every 2n tuple here, we have a 2n tuple in here. This means I can express the Hamiltonian as being a function of q's and p's, and I'm just going to say qp as a shorthand. All right. Now, our goal is to think of this function in its natural coordinates and start taking derivatives. Okay, so goal. Look at dh dqj and dh dpj. Remember that these are generalized, are the natural coordinates for h. Now, I'm going to borrow a bit of notation from other areas of physics. This is actually commonly used in thermal physics, and that's to subscript all of the coordinates that are being held constant. Remember from a vector calculus class that a partial derivative only makes sense if I tell you which coordinates are being held fixed. So in this case, we want to hold fixed the q and p coordinates, and not the q and q dot coordinates. That's going to become important a little bit later in our discussion. So again, just like here, I'm using this shorthand. I'm holding all of the q and p coordinates fixed except for qj. And here I'm holding all the q and p coordinates fixed except for pj. All right, so now let's do these one at a time. dh dqj while fixing the q's and p's. Well, all I'm going to do is act on these. And so I'll act on these. I can go right through this sum with my derivative, but then I'll need to use the product rule. All right, so let's do that. So first I get partial of q dot. Now, because of this assumption, I have that q dot, oh, and I shouldn't use j here because that would be, j is already being used here, so I'll use k. I know that qk dot can be thought of as a function of the q's and p's by this assumption. Okay, so I'm taking a derivative of that thing with respect to qj while fixing q's and p's. Then I'm holding pk constant in that term. And then next, I need to do the second term in the product rule. So here I'll hold qk constant. And then I'll take a derivative of pk with respect to qj while holding all of my q's and p's constant. Next, I need to subtract off the Lagrangian. Now here, I'm going to need to use the multi-dimensional chain rule. So let's do that right away. The chain rule is going to tell me that I need to take the Lagrangian with respect to each of its natural arguments, and then take the derivative of that argument with respect to qj while fixing q and p. Okay, so once again, I'll get a sum over k. Now, first, I need to take the derivative of the Lagrangian with respect to qk. So I'll get dl dqk, but this is fixing the natural coordinates for the Lagrangian, which are q's and q dots. So that's another shorthand that I'll use right here that matches this shorthand in sort of the way that it works. This means all of the q's and q dots except for qk. All right, and then now I need to take the derivative of that coordinate with respect to qj. So then I get dqk while of q dqj while fixing the q's and p's. Then I need to take the derivative of the Lagrangian with respect to qk dot while fixing the q's and q dots, and then take the derivative of that coordinate with respect to the one that I actually want. So once again, just like here, I'm going to note that qk dot is a function of the q's and p's, and then take a derivative with respect to qj while fixing q and p. Good, one more to close there. Now I have a bunch of simplification to do. So first up is to note that this here, oh, that's not coming out very well. Let's try this one. This here is the derivative of one coordinate with respect to the other coordinate. That is definitely going to be 0. Next up is that this thing here is the derivative of a coordinate with respect to a similar looking coordinate, but these are only the same if j is equal to k. So this turns into the Kronecker delta, delta jk. Okay? The last thing to notice is that this is actually the definition of the kth generalized momentum, pk. Okay. So now let's see what happens when the dust settles. All of this is now equal to what? So I get a sum over k, and I can just pull both of these sums over k together. So then the first term is dqk dot is a function of the q's and p's, dqj sub qp pk. This term is dead. This term here, well, we'll deal with that in a second because it can actually come out of the sum because of the Kronecker delta. Then this term here is, and I have a slight problem here. No, I'm good. Then this minus sign distributes here. So I have minus pk times dqk dot qp over dqj, fixing q and p. Okay, let me close that. And then outside of this sum, I have minus, Well, this is delta jk, and then the derivative of Lagrangian with respect to qk. All right, while fixing q and q dot. So let me leave that as it is for a moment. So that becomes qj after evaluating the Kronecker delta while fixing the q's and q dots. And look, these two terms exactly cancel. Okay, so we're left with just this term. Now what I want to do is use the Euler-Lagrange equation on this term. And why is that? Well, the Euler-Lagrange equation is going to tell me that this is actually related to the time derivative of the other part of the Lagrangian, I should say the Lagrangian with respect to the time derivative of qj. So this is all equal to minus the time derivative of dl dqj dot, fixing the q's and q dots. Again, because I'm using the Euler-Lagrange equation, this is really going to give me what the Hamiltonian is along the actual trajectory. So this is only pertains, once I use the Euler-Lagrange equation, to the actual trajectory taken by a particle. But that's okay, because that's usually what we're interested in. Now, as a last step, I'm going to note once again that this is exactly the jth momentum. So this is minus pj dot. Okay, interesting. So that turned out really pretty simply. Let's try this second one here. Okay, so here I want to do dh dpj while fixing q's and p's, and I'll just do exactly the same thing. So I'm going to come over here, and I need to take a derivative with respect to each of these in my product rule. So first I have the derivative of q dot k, q and p, with respect to pj, while fixing the q's and p's, and then I'll multiply that by pk. Then, because of the product rule, I'll leave q dot k alone and take the derivative of pk with respect to pj while fixing the q's and p's. Okay, that's one sum. Then I have minus, now I need to use the multidimensional chain rule on my Lagrangian again. So here I'll get a sum over k of, first, the derivative of the Lagrangian with respect to q, k, while fixing q and q dot, times the derivative of qk with respect to pj while fixing the q's and p's, plus the derivative of the Lagrangian with respect to qk dot while fixing the q's and q dots, times the derivative of qk dot fixing q's and p's, or in terms of q's and p's, with respect to pj, fixing the q's and p's. All right, once again, we can go searching for simplifications. Notice that here, like before, we get a Kronecker delta because it's a derivative of pk with respect to pj. Down here, we get a 0 because I'm taking the derivative of qk with respect to pj while fixing q's and p's. So this term is 0. Okay. And then, once again, I get the kth generalized momentum showing up. All right. So I bet it's not too hard to guess what's going to happen in this case, and it's very similar to the last case. First, I'll have my sum. Notice that this and this term will still depend on the sum over qk, so let's deal with those first. We get dqk dot, it's a function of q and p, dpj, fixing q and p, times pk, minus, because of that minus sign, pk times dqk dot, fixing q and p, with respect to Pj while fixing Q's and P's. Okay? And then in this case, we get plus Qk dot, and that's it. And I'll actually leave it here. I don't need to put the arguments in for reasons that we'll see in a second. Now, just like before, note that these two cancel. And so in the end, I just get that this is equal to Qk dot. Now, where do these equations leave me? Let's highlight what was important. So I have that this is equal to this, and this is equal to this. These two equations are called Hamilton's equations. Let me write them up. So let's do that one, and then this one. Okay, and I've dropped my subscripts that tell me what to fix. That's because, notice that by doing things in this way, I've eliminated all sort of reliance of my equations on the Lagrangian at all, or the Lagrangian's generalized coordinates. Now, everything only depends on Q's and P's. So I can solve for the trajectory in QP space simply by knowing the Hamiltonian, which is a function in QP space. By the way, we're going to need to name that space, so let me do it here. The space of all Q1 through Qn and P1 through Pn is called phase space. All right. So the Hamiltonian is a function on phase space. And in particular, we also saw that the Hamiltonian is typically the total energy. So the Hamiltonian is typically a function on phase space, which is the total energy, and which doesn't require us to go through this procedure to write down, because we know what the kinetic energy is. That will typically depend on the momentum. Let's start with a couple of examples where we can use Hamilton's equations. The first one, maybe the simplest thing we could imagine starting with, is the free particle. We'll do everything in one dimension because that will make things a lot simpler. Okay, in this case, the Hamiltonian is just going to be the total energy. The total energy of the free particle is given in terms of the momentum by p squared over 2m. If you're familiar with 1/2 mv squared, notice that these are the same thing. All right, so what do Hamilton's equations tell us? Well, the first one that we have written here tells us that dHdqj, which is 0, is equal to minus pj, oh, and I forgot my dots here, minus p dot. And the second one tells us that the derivative of h with respect to p, which is in this case just p over m, is equal to q dot. Okay, what does this mean? This tells us that the momentum is not changing. And momentum being conserved is exactly what we expect when there are no forces on the system. So it makes sense because the particle is free. This second equation tells us that p over m, in other words, v, is equal to the derivative of the position. So this tells us that we have constant increase in position. Good. All right, so that wasn't too bad. Now, how about another example? we can do the 1D harmonic oscillator. The harmonic oscillator is somewhat of a perfect case for using the Hamiltonian formalism. It makes a lot of sense in this formalism. Okay, in this case, we have that the Hamiltonian is, again, p squared over 2m is the kinetic energy, and then the potential energy is 1/2 m omega squared x squared. Of course, we could write this as kx squared, but omega ends up being the natural frequency root k over m if we do it that way. Okay, so once again, let's write Hamilton's equations. The first equation tells us that m omega squared x is equal to minus p dot. And the second equation tells us once again that p over m is equal to x dot. I've used x here, but I've used q elsewhere. Let me maybe switch to just stay with q everywhere. Again, q here just denotes the position. All right. Notice this is exactly Newton's second law in this first Hamilton equation, because the time derivative of the momentum is the force. And then this is the law that we saw above that tells us that the velocity is just the change in the momentum. But now we actually see kind of a nice way to deal with this using a technique that we learned about way, way back in one of our first lectures in the course. And that is the use of complex coordinates. To do that, first we're going to need to come up with a single unit that's going to be shared by both quantities. So in this case, the problem is that Q has units of length and P has units of momentum. To get from length to momentum, I need to multiply length by first 1 over time and then by a mass. So notice that m omega q has units of, or has dimensions of momentum. So what I'm going to do is define the following object. I'll let z be equal to m omega q plus I times p. Okay? That means that z dot is equal to m omega q dot plus I p dot. Now, let me use my two Hamilton equations here and figure out what this is in terms of q and p once again. Okay, so m omega q dot is going to be omega, yes, m omega q dot is going to be omega times p, okay, and then plus I p dot will be minus m omega squared times q times I. Great. Next, I'll pull an I omega out of this whole expression. That's going to give me I omega times m omega q a minus I omega out of this whole expression. That's going to give me an m omega q for that first term, and then plus, well, what do I need to put into the second term? If I want to get a plus 1, I need to multiply this minus I by a plus I here, so plus IP. But notice that this is exactly z. So I get minus I omega z. Wonderful. So putting this all together, I have z dot is equal to minus I omega z. And I know how to solve first order equations of this form. I get that z dot is equal to e to the minus I omega t times some z naught. Good. And by z dot, I mean z. Oops. So what I find is that with this choice, the motion that my object is making in z space, so this is the real part of z and the imaginary part of z, is just a circle of radius z naught. Let me say that's the absolute value of z naught. And so I'm moving clockwise in a circle of this radius. Good. Now notice that the real part of z is equal to m omega times q. And the imaginary part of z is exactly p. So whereas in this z space, I'm performing circular motion with this choice of dimensional constant, back in QP space, in phase space, the motion is going to be elliptical. And that's really super important because in general, when we have a confining potential like this, we won't get a nice sort of circular or elliptical potential for general potentials, but anytime we have a confining potential, we do have our object moving in closed loops like this. Let's think about why that is. Remember that h is conserved along the flow of the particle. In other words, h is conserved on the trajectory that the particle actually follows. That means that our particle moves along a level set of h. And the level sets of h can be mapped. Here in two-dimensional phase space, we have a two-dimensional phase space when we have a one-dimensional system. In two-dimensional phase space, the level sets of h look like one-dimensional curves. And if h is confining, which means unbounded above but bounded below, then its level sets are always closed curves. So that's pretty cool. Even though we don't know exactly the trajectory of a given object, we do know the image of the trajectory. This is really reminiscent of how we dealt with orbits. Remember, we couldn't solve our equations for r of t and phi of t separately, but we could solve an equation for r of phi. What Hamiltonian mechanics is telling us is that anytime we have a one-dimensional system with a confining potential, we don't know in phase space necessarily what the trajectory is, but we can find the image of the trajectory relatively easily, and that can be really useful. So this demonstrates another of those big power uses of Hamiltonian mechanics. All right, before we go on, I actually want to look at one more thing a little bit more closely. We mentioned that the Hamiltonian can be thought of as a function on phase space, and that level sets of that function can tell us about the image of the trajectory of an object over time. So let's imagine that we have the following situation, which I'm going to expound on here in Mathematica. Let me increase the font size a little bit so it's a little easier to see. Let's imagine that we have a one-dimensional system and that the Hamiltonian is a function of q and p. Well, for p, we typically get p squared over 2m. Just so that we can plot things, I'm going to let this be p squared. Somehow I'm absorbing, let me say p squared over 2, actually. I'm absorbing the factor of m into my dimensions. Oops. And then I need to decide what kind of potential I'm looking at. Well, we've already seen what happens with a quadratic potential with the harmonic oscillator. So let's do something different. Let's look at a quartic potential. So in this case, I'll say 1/4 q to the 4th. Again, I'm going to absorb what I would normally have, the coefficient, into my dimensions here so that everything is actually dimensionless. All right. Now I want to look, first of all, at just a plot of this object. So let me plot h of qp, and I'll look at both positive and negative q and positive and negative p. So let's say maybe -3 to 3. Oops. And p can also be -3 to 3. All right. And what we see in this case is that because our potential increases, or not our potential, sorry, our Hamiltonian increases unboundedly in both the q and p directions. Basically, whatever direction I choose to go from the origin, my potential eventually gets very large. My level sets will end up being closed curves. But what will be the shape of those closed curves? Well, it's actually easier to see that if I do a contour plot. And I'll just have it over the exact same range. So that in this case, my trajectories will be closed curves around these contours. Again, trying to figure out what q will be as a function of t or p will be as a function of t will be hard. It will require solving difficult and sometimes nonlinear ODEs. But trying to figure out what the image of the trajectory will be is relatively easy. And so in particular, we can see that in this case, the orbits will be bounded. Will never get larger than a particular q value or smaller than a particular q value, and will never get either larger or smaller than a particular p value either. All right, let's do a second example before we jump on to something else. Let's look at a case where the orbits are not bounded. So here, I'll think about the case where we have, rather than an object on some sort of strange spring or some sort of strange confining potential, let's think about a case where we have a proton, or just a positive charge, approaching another positive charge. In this case, well, we know that once again we'll have p squared over 2 for our kinetic energy, but now we'll have a potential energy which is proportional to 1 over q. And once again, I will just make everything dimensionless by absorbing constants. All right, great. So let's do that. And now let's do the exact same thing. We'll use both of these functions here. So first, let's look at the 3D plot of this. And so in this case, look, our level sets, well, for one, they're going to be discontinuous because I have this asymptote at q equals 0. At q equals 0, my Hamiltonian function blows up either to positive or negative infinity. Actually, I'm realizing that here I should have had the absolute value of q. Sorry about that. So it should be positive infinity in both cases. Good. Now in the p direction, I do have what looks like an increasing function in both directions, and that's because of this p squared here. All right, now let's look at the contour plot. And so here we see that our trajectories will be unbounded, and this is already very useful. We know that the particle will travel in QP space. Maybe I should label my axes here. Now if I label my axes, that's a little better. We see that in Q space, I have orbits which are unbounded. They'll eventually go from positive infinity over here towards 0, possibly, and then out again away from 0. So all of the possible level sets are unbounded in this case, and that tells me I have unbounded motion. So the Hamiltonian approach is already very useful if we want to heuristically figure out what the motion of the object will look like over long periods of time. Okay, now on to something else. Next, I want to deal with something a bit different. Consider a function on phase space. In other words, f of q's and p's is some real. Well, I could ask the following question. What is f of t, which is defined to be, this is an abusive notation, f of q1 of t through qn of t and p1 of t through Pn of t. In other words, this function is just static. It's defined on phase space. But if I start following the trajectory and reading off at every time what the value of f is for the particle's position in phase space at that time, then I'll get some function of time, which I'm also calling f. A little bit of abusive notation there. Well, let's see if we can figure this out. In particular, I don't know that I'll be able to find this, but maybe if I take a derivative, I can find something. So let's note that f dot of t, well, in order to take that, I'll need to use the multidimensional chain rule again. So I need to take a derivative with respect to each one of these arguments, and then a derivative of that argument with respect to t. Okay? So I'm going to plug this in. I'm going to sum over k, and then I'll get a derivative of f with respect to qk, and then a derivative of qk with respect to t. Next, I need to take a derivative of f with respect to pk, and then a derivative of pk with respect to t. But now, what I'll do is I'll use Hamilton's equations to plug in for those two values. So again, for qk, I'll plug in this positive derivative of h, and for pk, I'll plug in this negative derivative of h. Okay, so this is going to give me this sum over k of df dqk times dh dpk minus df dpk dh dqk. Okay. And this is going to motivate me to define some kind of thing, some kind of object that takes in two functions and spits out this quantity. So this motivates me to define the so-called Poisson bracket. After Siméon Denis Poisson, a French mathematician of the early 19th century. All right. Okay, so this bracket takes in two functions and spits out another function. And it's defined as follows. The bracket of f and g is the function defined by the sum over k of df dqk dg dpk minus df dpk dg dqk. And in particular, this tells me the thing that I was already after in the beginning, which is that f dot is equal to minus the Poisson bracket with h. Cool. The Poisson bracket of h with f, I should say. Good. Okay. Sometimes, in order to say this, I will say h bracket f. That's another way to say it. This bracket turns out to give me more information than just this time derivative, though. In particular, let's check qj bracket pk. Okay. Now I'll need to make my sum over something else. So let's use L. So I'll get dqj over dql times dpk over dpl. Oops, messed that up. Okay, minus dqj over dpl, dpk over dql. But for both of these factors in the second term, I get 0. So that's definitely 0. And here I get two Kronecker deltas. So this becomes the Kronecker delta of J and L, and the Kronecker delta of K and L, but inside of sum over L. The rule there is that I can, for instance, use this Kronecker delta to kill the sum and set that L to a K. So I get the Kronecker delta of J and K. Okay, so I have two functions, I should say, such that their bracket, their Poisson bracket, is this Kronecker delta like this. Any set of 2n functions satisfying this condition is called a set of canonical coordinates. So I'm going to say qj union pj is called a set of canonical coordinates. Great. So this bracket comes up in this context as well. Now, next, I want to use a little bit of space to go over some other properties of the Poisson bracket. And let me first just list them. All right. The first one is that the bracket is linear. So if I have G plus H here, I get Poisson bracket of F with G plus Poisson bracket of F with H. And that comes straightforwardly from the linearity of the derivative. The next is that if I have a number, C, and I stick it in here, well, C can just come out. Where does that come from? Well, if I stick CG in here, the C can once again come out because of the linearity of the derivative. The next one is less sort of straightforward. It's that F bracket G is equal to minus G bracket F. Okay, this is very important. It means that this bracket is a kind of antisymmetric product, maybe not unlike the cross product that you've already met elsewhere in mathematics. Where do I get this? Well, it comes exactly from this minus sign. Notice that if I swap F and G in this first term and in this second term, well, I can also just swap the terms around at the cost of a minus sign. All right. The next one is also a big deal. Suppose I stick in a composite object, G times H, in the second term in my Poisson bracket. What's that going to be equal to? Well, it turns out that the Poisson bracket is a kind of bracket that satisfies what's called satisfies the product rule. Mathematicians would call this a derivation. Okay, so what is this? It's going to give me F bracket G times H plus G times F bracket H. The order doesn't matter because these are just ordinary functions, but I've left it in this sort of order here where I've put H on the right here and G on the left here, just to remind you of the product rule. Now, where does this come from? Well, notice that I put G times H in here. I really do get the product rule. And the product rule just comes out such that I'll get an H out in one term and a G out in the other. Okay, so this is quite important. Now, lastly, there's a rule called the Jacobi identity that has to do with doing this 3 times. So let me give that to you. I should say doing it twice. So bracket F bracket G bracket H plus, I'm going to do this cyclically now, G bracket H bracket F plus H bracket F bracket G is equal to 0. Now, we're never going to use this, but I just wanted to note that this property, this property, this property, and this property turn this structure, the set of functions with the Poisson bracket, into something that mathematicians call a Lie algebra. And that gives it all kinds of really interesting and nice properties. This is more of just a sort of keyword for you to look up if you're interested in this kind of thing. The sort of fundamental mathematical physics text on this is V.I. Arnold, if you're interested. Okay, I'm going to erase the board, and then we'll move to the computer to do a couple of examples. Now, I want to hop right into our main example here. And before we do, let me make sure that I relist the set of assumptions that we have, or not assumptions, properties that we proved of the Poisson bracket. Okay. So the first, the first is that the Poisson bracket is a linear function. So f g plus h is equal to f bracket g plus f bracket h. Second, f bracket c times h, if c is just a number, is equal to c times f bracket h. I don't know why I used h here. Let me turn that back to g. Third is that it's anti-symmetric. So f bracket g is equal to minus g bracket f. Just to be clear, by the way, about what I was saying before, these two together imply that it's linear. And the last two are a little bit more complicated. The first, which we'll actually need, is that it's what's called a derivation, which means that f bracket gh is equal to, well, first we're going to imagine acting just on g and then having h outside. Then we'll move g to the left and we'll imagine having f acting just on h. So f g h plus g f h. So we can say acts as a derivation. That's just a formal word from math. And I'll also put in parentheses, this is the product rule. This is the easy way to remember it, that this is some sort of generalization of the product rule. The last one is the Jacobi identity, which we won't need, but I will list here. We had it on the last board. Okay. So let me just mention that these are the properties. Okay, and I want to use this to try to figure out the dynamics for the following system that we definitely know how to treat already. Let's do the 2D harmonic oscillator. So h will be px squared over 2m plus py squared over 2m plus 1/2 m omega squared x squared plus y squared, that whole quantity. Okay. Now, I definitely could jump in and start solving Hamilton's equations. I've already given an example of how you do that for the 1D harmonic oscillator, and it would be very similar here. But we have a different way of proceeding because we know, recall, for any function f, that the time derivative of f, and let me just be clear what I mean here, d dt of f of q of t, p of t, which we'll denote by f dot, is equal to minus the Poisson bracket of h with f. So we actually have a quite easy way of treating systems like this. By ignoring Hamilton's equations, strangely enough, and instead thinking of other functions for which we can find the dynamics. All right, let's do that. So the first thing is that I kind of have a guess from Lagrangian mechanics about a conserved quantity. Recall that because the system is translational or is rotationally invariant, I expect that the z angular momentum is going to be conserved. So that would be Lz, which is xpy minus ypx. Okay. So let's just check. What is Lz dot? Okay. Well, I know that in general this is the Poisson minus the Poisson bracket of h with Lz. And I think that the way to start is just to write that out. It'll be long, but I can reduce it by quite a lot. And we'll see how that works in just a second here. Okay, so we'll have a big minus sign on the outside. Then we'll have px squared over 2m plus py squared over 2m. I guess we don't need this parenthesis here. Plus 1/2 m omega squared, quantity x squared plus y squared. And we're going to take the Poisson bracket with x, p, y. Oh, and I've forgotten a factor of m here. Oops. But I know that since m is just a number, by my property, what was that? 2, this comes out. So let me just put, this is by property 2. Maybe I should copy these numbers up here. So this is going to be 1. This will be 2, 3, and 4. We won't need this one down here, but I guess I'll just give it a number as well, 5. Okay, and then where was I? Minus ypx. Let's recall also that we already know a couple of Poisson brackets. In particular, we know let's say we know xy is equal to 0. We know that px, py is also equal to 0. And then that x, px is equal to 1. And y, py is also equal to 1. So we'll be able to use those in order to reduce this expression. Okay, let's use linearity to break this up into a whole bunch of sums. It's going to be rather gross. It'll be 8 of them, but we'll be able to reduce them in just a minute. Okay, so first, let's do the first 4 that correspond to this. So let me point out, I'm going to use rule 1 here. Okay, so we'll get minus px squared over 2m, actually, 1 over 2m, bracket px squared x py, minus m times 1 over 2m, bracket py squared with x py. Next, we get minus m times half m omega squared, bracket x squared with x py. Then we get plus, and by plus I mean minus, minus m times half m omega squared y squared, bracket x py. Okay, that's the first 4. Now for the next 4, I'll just switch xpy to minus ypx. Okay, so then I get plus m times 1 over 2m, bracket px squared, ypx. Then I'll get another plus m times 1 over 2m, bracket px squared with ypx, plus m times half m omega squared, x squared, bracket ypx. Okay, and then plus finally m times half m omega squared, y squared, bracket ypx. Now the thing that's really going to simplify our lives here is that a ton of these are 0. They're 0 anytime none of the objects inside of the bracket have non-zero bracket with each other. So we'll only get a non-zero answer or let me say a non-zero term if bracket includes x and px or y and py. Otherwise, it's definitely going to be 0. So here's an example of one that is not 0, and it's because there's an x in one term and a px in the other. So that'll stick around. But in this one, for instance, we have py in both, but then with x. So there will be no term that survives here. That's going to be 0. Similarly, in this one, we have x and py, but no x and px or y and py. This term, however, will survive because we have both y in one factor of the Poisson bracket and py in the other one. Okay, good. Now down here, this term dies. This term dies. But then this has x and px. And this has... Oh, and this shouldn't die. I just copied wrong. Sorry about that. That should be py, and then this survives. But this term does die. Okay, next I'm going to only care about the ones that I didn't cross out, and I am going to use what next? I'll use rule 4 to reduce this. So let me use rule 4 first on the right. And I'll also get rid of clean up some of this. So like, for instance, minus m times 1 over 2m is just minus 1/2. Okay, so we'll get minus 1/2 px squared bracket x times py plus x times px squared bracket py. Okay, that'll be one of the 4 terms. Next, we'll have another term at the end here. This one will be minus 1/2 m squared omega squared. Now I'll get y squared bracket x times py, plus x y squared bracket py. Okay. Next, I'll go down to this term. This is going to give me a plus 1/2. Then I'll get py squared bracket y times px plus y times bracket py squared px. Good. And then finally, I'll get plus 1/2 m squared omega squared x squared bracket y times px plus y times x squared bracket px. Now I'm going to go through another round of cancellation using this rule here. So a bunch of these terms also cancel. Notice, for instance, this term cancels because it only has p's in it. That one is gone. This one only has position terms in it, y and x. So that's gone. This term only has p's, and this term only has x and y. So those are all gone. Now, I need to do one more thing, which is I need to combine 2 of the rules here. If I combine both rule 3 and rule 4, I get a sort of extra rule, so 3 plus 4, which is that I can first, if I have GH bracket F, I can say this is minus F bracket GH. Then I can split it as I would by rule 4. So that gives me minus F bracket G on H minus G times F bracket H. And then I can put them back in the order I started. So this is now itself equal to G bracket F times H plus G times H bracket F. Okay, so I also get some sort of product rule in the other direction if my composite term is in the first part of the Poisson bracket, not the second part. Okay, let's go down here and use that. So here by, again, rule 3 plus 4, I can split up all of these terms. So I get minus 1/2. Now px squared is going to give me px times px bracket x plus, well, just another copy of that exact thing, px bracket x times px. Notice that I'm moving this to the other side so that we can remember it kind of using the product rule, but it actually is just exactly the same. This is some function and this is some function, and we're just multiplying them. So I could also write 2 times px bracket x. Okay, let's keep going. Next we get minus 1/2 m squared omega squared times, oh, and what have I done here that's not smart? I forgot to pull out my py. And in this case, I need to pull out my x. Okay, now I get y times y bracket py plus y bracket py times y. Good. Okay, third term, here I'm going to pull out a px, so I get plus px over 2 times py bracket pyy plus pyy bracket y, and then another plus 1/2 m omega squared. In this case, I get y times x, x bracket px plus x bracket px times x. And actually notice that in all of these cases, the 2 terms in the parentheses are exactly the same. So I just get them doubled. But also in all of these cases, I can reduce them using the rules right here. So let me actually mark these, in green, to note that these are the ones that I'm going to use below. Okay, so this one by the green rules is minus 1. Maybe I'll use blue up here just to be clear about what I'm doing. By the green rules, this one is plus 1. This one is minus 1. And it's minus or plus just based on whether or not the momentum is first or the position is first. Okay, and then finally, this one, is plus 1. Okay, so now just reducing this further, I'm going to get minus, so notice the fact that there are 2 in each set of parentheses is going to cancel the 2's on the outside. So for the first one, I'm going to get plus, because minus 1 times this minus sign here, so plus px times py, okay? Then here, I'm going to get minus m squared omega squared xy. Then for the third one, I'm going to get minus px times py. And for the fourth one, I'll get plus m squared. Oh, did I miss a squared? Yes, I dropped a squared here. M squared omega squared xy. Oh man, but check it out. Look, this term cancels this term, and this term cancels this term. So in the end, my whole thing is 0. What I've proven is exactly what I already knew from Lagrangian mechanics, but it's good to show that it works here too, which is that LZ dot is equal to 0, or LZ is conserved under the dynamics. Okay, it's already pretty cool that we've been able to see that LZ is conserved just by this Poisson bracket argument. But we can actually use this to clean up our solution for the dynamical equations. So let's go back to Hamilton's equations, but we only need 2 of them. In particular, we know that x dot is equal to minus h bracket x. Just to remind you how we get that, let's do this little calculation over here. The only part of h that matters for us here, so minus h bracket x, the only part that matters is the px part on the left, because that's the only part that's going to have a non-zero bracket with x. And by everything we saw above, it's actually possible to show, without too much difficulty, that this is just px times 2 times px times px bracket x. And when all is said and done, this is just px over m, this whole expression. Okay, so this is px over m, and by the exact same argument, y dot is equal to py over m. But notice that this is only 1/2 of Hamilton's equations. We have not used the Hamilton's equations, or the Hamilton equations, for the momenta yet. But let's use the fact that we know that LZ is conserved. LZ itself is x times px, x times py minus y times px. Now it's quite helpful that we now know that LZ is conserved, because now we can start replacing LZ in some of our equations. And in fact, there's another quantity we know is conserved. It's precisely the Hamiltonian. So h is px squared over 2m plus py squared over 2m plus 1/2 m omega squared x squared plus 1/2 m omega squared y squared. So what would be nice is if we could solve for px and py in terms of xy and then these two constants of the motion. So let's start that process. Now it's a little bit gnarly, but we can do it. To start, let's start by solving px in terms of everything else. Okay, so we get px is equal to 1 minus 1, over y times LZ minus xpy. Okay, great. So what I'm going to do is stick that in here. H is now equal to 1 over y squared LZ minus xpy quantity squared times 1 over 2m plus py squared over 2m plus 1/2 m omega squared x squared plus 1/2 m omega squared y squared. Good. Okay, now my goal here is to solve for py in terms of everything else. All right. And that I'm also going to use to stick back into this equation for px. So notice that now I have an equation that just involves py, y, and x, and h and lz, but those are constants of the motion. Okay, let me expand the right-hand side. So I'll get 1 over y squared times lz, lz squared over 2my squared. That's probably a nicer way to have it. And then minus, I'll get a 2 from the fact that it's a cross term. Then I'll get lz xpy over, the 2 in the numerator will cancel the 2 in the denominator. I'll get my squared. Okay, pretty good. And then plus, now I'll get x squared py squared over 2my squared. Okay, great. Then I get my py squared over 2m plus 1/2 m omega squared x squared plus 1/2 m omega squared y squared. Now let's get this into its final form before we move on. Okay, so what I want to do is move everything to one side of the equation and group my terms based on the order of py. Okay, so the py squared term is going to combine these two. So I'll get 1 plus x squared. I should have pulled out the 1 over 2m first. 1 over 2m times 1 plus x squared over y squared times py squared. Okay. Next, I have my linear term in py, which is this one right here. So minus lz x over my squared times py. And lastly, I have my term that does not depend on py at all. And that one is going to be lz squared over 2my squared plus 1/2 m omega squared x squared plus 1/2 m omega squared y squared, and then minus h. All of this together is equal to 0. Okay, let's group these terms because in the end, it's okay to just sort of do things in this way. So this will be a of xy, b of xy, and then all of this together will be c of xy. And I know now that py is equal to, well, just the quadratic formula, minus bxy plus minus square root of bxy squared minus 4axy cxy all over 2axy. This allows me also to figure out what px would be. Notice that px is given by this, so I would get minus 1 over y times lz minus x times all of that stuff. And because I have copy and paste here, to make my life really pretty easy, all right, so what's the idea here? Now I can rewrite my two Hamilton's equations simply using things that depend on x and y. 1 over m. So I'll just write here px of x, y, l, z, h, and this one is 1 over m py x, y, l, z, h. Okay. Now, in this circumstance, this is much harder than solving Hamilton's equations. But imagine that we had been dealing with something that was a lot more complicated than the harmonic oscillator, but that still had rotational symmetry. So imagine we had h was some complicated px squared over 2m plus py squared over 2m plus some complicated v of xy that still had rotational symmetry. So that we still expected LZ to be conserved. Well, then this might be our best bet. This might actually be nicer than Hamilton's equations. So solving in this way, possibly numerically, might be our best bet. Great. Okay, I'm going to hop back to the board so we can do a little bit more work there. Okay, we've gotten some basic familiarity with Hamiltonian mechanics now. First, we introduced Hamilton's equations and showed that we can use them to produce systems of first-order ODEs that we can solve for the trajectories of objects. We introduced the concept of phase space, and we showed how the Hamiltonian maps out certain level sets in phase space to which the system is constrained. Next, we introduced the Poisson bracket. The Poisson bracket tells us about how the values taken by functions over time, if those functions are on phase space and we sort of read them out as the trajectory of the particle sort of moves around, how those functions' values evolve over time as well. But this leaves some big questions left. In Lagrangian mechanics, we had a really, really nice way of including symmetries in our problems. Namely, if we could find a system of generalized coordinates that respected the symmetry, so if we could find a system of generalized coordinates such that the Lagrangian did not depend on qj for some j, then we knew that the generalized momentum, pj, was a constant of the motion. In Hamiltonian mechanics, we have not yet gotten there. Now, the other thing that we haven't really gotten to is talking about phase space a little bit more geometrically and about how the particle sort of flows around under the Hamiltonian on phase space. To do that, next time we're going to talk about the Hamiltonian vector field. I hope to see you in that one.